Hey everyone, welcome back. Today we're going to be looking at the area and volume problems, the types that were kind of really popular with the AP test about 10 years or so. That's 10 years ago or so. But now we're going to take a look at area as it happens as cross-sectional area, or the volume as it happens where you have the same cross-sectional area. And then we'll see a couple of things that you can do with those volumes, and let's get started. So we're back on Tron. We're on the remake of Tron this time, which is from 2010. And the whole idea is, you see the tower on the left side. It's a very tall needle-like tower. And I'm wondering, let's say let's try to model this mathematically. And so we have this triangular shape, which will serve as the base of our region. And then from that, we're going to build out cross sections perpendicular to the y-axis that are squares. So you can imagine a whole bunch of squares lining up perpendicular to the y-axis up all the way to the top of this tower. So here's our problems. A, write but do not evaluate an integral expression that gives the volume of the tower. B, the tower is to be filled with energy streams, which is liquid energy. Just think water and you'll be fine. And it's going to be filled from the bottom up so that the liquid in the tower is given by this polynomial expression 1/300th h cubed minus 18h squared plus 108h, where h is the height of the liquid energy. If the rate of change of the height with respect to time is dh dt is 1/5 root h, what is the change in the volume of the liquid energy when h equals 3? And then finally, at t equals 0, the height of the liquid energy is 0.36 units. Use the separation of variables technique to find an expression for h in terms of t. So let's get at it. Let's look at letter A, write but do not evaluate an integral expression. So we know our cross sections are perpendicular to the y-axis. So, and we know that they're squared. So we can take a look at this as, well, the y-coordinate is given as 6 minus 10x. And if you solve, you get that the x-coordinate at any point y would be 1/10 6 minus y. And that's important to us because if you remember, we're going to be finding the area of each cross-section. And the cross-section is the distance from the left side of the tower to the right side of the tower. Looking at this slide again, you can see the square is going to be built by the difference of these two x-coordinates here. So let's say when y equals 2, the side of the square will be here at where the red line is, and then the other end of that will be here at the y-axis. Okay, so now that we have that, we know the cross-sections are square, so let's find the area of each cross-section with respect to x. And if we know that the area is s squared, and the side of the square is going to be the same thing as the x-coordinate squared. Well, the x-coordinate is just given by that 1/10 6 minus y squared. So then you get the area of any cross-section along the y-axis can be given by 1/10, or the quantity of 1/10 6 minus y squared, which would be the square of the x-coordinates, or the difference of x-coordinates. If you like, you can simplify that. 1/10 6 minus y squared. Now we're just going to go ahead and start with our integral. We know that volume is the area, or the integral of an area formula. And our area formula here is 1/100th 6 minus y squared, integrated from 0 to 6. Now, I believe this is the integral expression that will give us the volume of the tower. So this problem really is finished, although this is such an easy integral. I don't know why you wouldn't just finish it anyways. So you get a volume of 0.72 cubic units. Well, that takes care of part A of our problem. Remember that when you're trying to find volume, it really just is the integral of an area formula. So the whole trick here is to find that area formula, and most oftentimes your area formula is going to be, or is going to involve the distance between two curves, so an f of x minus a g of x, or maybe an f of y minus a g of y. Maybe it's an f of x minus 0, or f of x minus some other constant. We'll see. Let's take a look at our next one. Our tower is going to be filled with those energy streams now, or the liquid energy. And if you're not paying attention to this problem, you probably aren't going to see that we're looking for dv dt. And our problem is that our equation for volume is in terms of h. So we need to somehow take the derivative of a formula in terms of h and take the derivative with respect to t. That's going to involve using the chain rule. So you see over here in the hint, dv dt is dh dt, or dv dh, multiplied by dh dt. Let me say that again. dv dt is dv dh times dh dt. So let's take our volume formula. Here we go. And we'll take a derivative with respect to h, and then we'll multiply that by dh dt. This is nice because we know the derivative in terms of h is a pretty easy thing to do. I mean, it's just a polynomial. I mean, you have the 1/300th in the front, but that doesn't mean anything. It's just a constant multiple. So that gives me, after I take my derivative, this 1/300th 3h squared minus 36h plus 108 multiplied by dh dt. What do you do with dh dt? Well, dh dt, they give it to you. It's just 1/5 root h. I think you'll see that right up here, 1/5 root h. So now that you have a dv dt, and it's totally an equation in terms of h. So at this point, you would just substitute 3. Do some calculator work, and you get 0.04024. Write that as a sentence to summarize, and you get when the height of the liquid energy is 3, the volume is increasing at a rate of 0.040 cubic units per unit of time. So there are no units here given to us, which makes me think that you probably wouldn't need to write the units. Just saying 0.040 would probably be enough. But we're trying to be complete here. So let's move on to letter C. And you got when t is equal to 0, the height of the liquid energy is at 0.36. We're going to use separation of variables to find an expression of h in terms of t. So we're going to need an equation for h, or dh dt, or an equation that has h and a t in it. And the only one that you have that is both h and t is this one. dh dt is 1/5 root h. Separate the variables. So in looking at this, you can see a dt on the denominator. So you're going to multiply both sides by dt. I also see the 1/5, or I say the 1/5 root h. Leave the 1/5 on the right side and divide both sides by root h. So we got dt over root h being multiplied on both sides. And that gives us that 1/5, or dh over root h is equal to 1/5 dt. And I like to keep that constant with the independent variable as much as possible. To help us take the antiderivative of this, we're going to change that to h to the negative 1/2 power dh. And now we just got to integrate. Let's integrate. And then we get 2 root h equals 1/5 t plus c. Make sure you're putting in your constant immediately. You don't need a constant on both sides. You just need to put a constant on one side, preferably with the independent variable. And now we just have to solve for h. Here, set up for solving for h. Here's our equation. Divide both sides by 2, I think. Here we go, 1/10 t plus c. You might be thinking c, shouldn't that be c divided by 2? Well, c divided by 2 is just another constant, so we'll just leave that as a c. And then we're going to square both sides, so h is equal to the square of 1/10 t plus c. Now finally, we are given what's called an initial condition, so we're just going to substitute that in there. And I think that says that when t is 0, you're going to have an h of 0.36. So here's our equation. And this is nice because 0 times 1/10 is just 0. So you'll get c squared equals 0.36, or c is 0.6. And now remember, you're not done yet. The product here is going to be an equation for h. So let's get our equation. H is equal to 1/10, or the square of 1/10 t plus 0.35. Technically, you're finished here. This is the end of the problem. You don't have to simplify further, especially for the AP test. But I'm seeing that you could, probably factor out a 1/10 to make this look nicer. So I just went ahead and did something a little extra. So we got 1/10 of the quantity t plus 6, that whole thing squared. And then, of course, 1/10 squared is 1 over 100. So here is our equation for h. Probably find that that's a lot easier to compute than 1/10 t plus 3/5 whole thing squared. I'm also noting that it's missing a square over there, so don't get confused. It'll be a square when you look at the answer key. There we go, much better. This brings us to our important ideas. So the really important idea here was the volume by cross section. So remember, you're just taking the integral of an area formula. Specifically, if your cross-sections are perpendicular to the x-axis, then you're integrating an area formula in terms of x. And if your cross-sections are perpendicular to the y-axis, like ours were, then your cross-sections are going to be in terms of y. So go ahead and pause it here for a couple minutes if you would like to copy these down. Then we'll move on. Here's our check your understanding. You've got a region bound by the two curves f of x and g of x. Notice real quick that f of x is this function down here that I'm highlighting in red. There's my f of x. And then my g of x, well, the g of x is going to be this top curve over here. This is that 4 times cosine. A good way to tell is that, well, you know that the cosine function starts at x equals 4 because you have 4 cosine. And you also know that the cosine function is inflected downwards. Or, I'm sorry, not inflected, but it has negative concavity. So the first part you're going to write but not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the line y equals 4. And secondly, you're going to say that the region r is the base of a solid. Each cross-section perpendicular to the x-axis is a square. So we're going to write but not evaluate an integral expression that gives us the volume of the solid. Let's get started with part B. So since we're rotating around an axis, our first question that we want to ask is, well, what kind of shape are we going to have? Is it going to be a washer or is it going to be a disc? And I always like to answer that question with, was one of the boundary curves of the region, was that actually the axis of rotation? And of course it wasn't. Both of the boundary curves were, well, curves. And the axis of rotation is always a straight line segment. So that means that we're going to have some kind of a washer. Take a look at the region and identify the axis of rotation first. There's a line, y equals 4. And we're going to try to figure out what is the equation for the big radius and what is the equation of the smaller radius. So our larger radius is the difference or the distance from the axis of symmetry to that function on the bottom, which we just said was f of x. So here we have our large radius is the axis of rotation minus f of x, which is just going to be 4 minus f of x. Now our smaller radius is going to be the same, except we're going to go to the closest curve, which happens to be g of x. So we've got a small radius of axis of symmetry minus g, which is 4 minus g. Here we go. 4 minus f of x, 4 minus g. Of course, since f and g were defined as part of the problem, you don't need to write out the entire equation of those. You can just write f and g and you'll be good. Here's the general volume formula for everything. Always start with that. The volume formula is the integral of an area formula. What is our area formula? Well, it's the area formula for a washer, which is pi r squared minus pi r squared. Substitute the pi r squares and use your calculator to integrate that, and you get 57.628. So here we have it with a nice sentence here. The volume of the solid is 57.628 cubic units. Which brings us to letter C. Now in C we're looking at cross sections that are squares, and first question is which axis are they perpendicular to? And they are perpendicular to the x-axis, which means that our equation should be dx. Everything should be an x in this equation. So what is the area of a square? Well, the area of a square is simply the side squared. And in terms of these questions, the side is always going to be the function on top minus the function on bottom, which in this case is going to be g of x minus f of x, if you'll remember from the beginning when we identified which one was which. Here's that general area formula that works for any time we find an area by integration. But this time, the area formula is s squared. And what is s? Well, s was just g of x minus f of x. So here's our volume formula. I'm noticing over here that this upper limit should be a 2. So something like that. And from here, you can just integrate on your calculator. Actually, I don't think we were required to integrate, but with a calculator in our hands, it's not really all that difficult. So we got 8.50314. The volume of the solid is 8.503 cubic units. So that's the end of our second day of area and volume. And hopefully these will help you out. Remember, for every area formula, you're only integrating, for any volume formula, you're integrating an area formula. There isn't a pi in every equation. That drives me crazy every year. But I'm going to let the calm take over. And I'll see you guys next time.